All right, guys, I think we get started. I will quickly finish the parabolic and hyperbolic trajectories, orbits. Actually, we have to start them yet. But I want to possibly finish them in a few minutes, well, half of the lecture, so that I can show you homework, uncollected homework 1. How many have done it? You haven't? Again, that's on you. I can't give you more than homeworks to do. Then you have to solve them. If you don't, then it's on you. So if you have solved it and you've done it correctly, you'll be in great shape for homework 1. If you haven't, maybe you'll still be in great shape. I can't guarantee. So these are just suggestions. I can't do more than that. So homework 1 will be, as I told you, Matlab files that you have to develop, maybe a few papers that you can scan and turn in as well if you feel like you need to. But it's mostly asking you to do this and this and this in Matlab. So it will be M files. You can upload on Canvas. The TAs will see it. I will post the solution as an M file myself, so you can start seeing what you've done, right or not, right away. So it should be pretty straightforward. I don't know how much time that will take, because Patrick is still sick, really sick, but hopefully they will turn them around quickly. All right, so parabolic trajectories. Now, I'm not going to, or orbits, I'm not going to prove that these are parabolas and after these hyperbolas, because the procedure is the same we followed for elliptical trajectories. You use Cartesian coordinates and you locate the position of the spacecraft with x and y and prove that you get actually the expression for a parabola or a hyperbola. So for this case, we have E equals to 1, and your Keplerian orbits parametric expression will look like this, obviously. The E goes to 1, which means that if we want to be formal in the way we write things, that the limit for the true anomaly that goes to pi of r, which is a function of theta, is plus infinity. So now you don't get a closed curve anymore. This doesn't come back. Okay? What else do we need to say about these? Well, I'll jump to, again, I'm not going to prove that this is a parabola, but we do know that all these curves we're getting, so this is the line of ups, they are all symmetric with respect to this line. And what I know is that if here is my attracting body M1, the Earth, here I'm getting something that eventually will go to plus infinity, right? So I may come from this other side. So the trajectory itself, it's symmetric, but you may start your satellite here, and it will eventually go to plus infinity in that direction. The energy is, in general, this expression. See how we found it? Yeah, with the h, 1 minus e squared, and in this case is 0, which means since energy is defined as kinetic energy minus potential energy, that this is always 0, right? Remember, this is the definition of mechanical energy per unit mass, and then for Keplerian orbits, we have proven at some point that this is what you get. You can actually write it as a function of h and e, but that's the initial definition is still this. So what this means is that the velocity at each point of the trajectory is what? Is the square root of 2 mu over r. This is always true. So it doesn't matter where you are, that relationship holds. It doesn't matter if you are at this r here or at this other position here, that is always true. And what happens when you go to infinity? It goes to 0, right? So this expression here has a definition, as a name. This is called escape velocity, v escape, because this is the velocity that you need at a certain distance from the attracting planet. So here you have your spacecraft M2. If you are at some distance r and you have that velocity, it means that you are on a parabolic path and you are coasting to infinity eventually, and you will get there with 0 velocity. Now recall that the little r and little r dot vectors, or v as we called it as well, these are relative position and relative velocity. So the spacecraft is going to approach infinity with respect to the Earth, for example. This is the Earth here, with 0 relative velocity, okay? So that means actually that the spacecraft is going to have the same velocity of the Earth when it's done with its parabola, eventually. Does it make sense? If you don't have velocity, relative velocity with respect to an object which is moving, it means you're moving as that object. So if you want to escape the planet, want to go away, never come back, you put yourself on a parabolic path, and you will eventually actually fly around the sun as the Earth is doing. That's what happens when you go on parabolic trajectories. Yeah, now you're not going to have a residual velocity that can allow you to go, for example, and travel to another orbit, to another planet. That will be a hyperbolic trajectory, as we'll see. So there is no excess, as we'll call it, speed. You get to infinity and you stop, and you start flying like the Earth. So that's what a parabola does for you. That's the escape velocity. Now, one thing that we may find interesting is that if you recall the circular velocity, if you are in a circular orbit, is actually the square root of mu over r, right? So v escape from this is also square root of 2 v circular. And at this point, you should have grown used to me saying we maneuver, we haven't done maneuvering formally yet. But I mentioned several times that we can assume that powerful thrusters can give you impulses that change your velocities very quickly. And so if you imagine that you are on a circular path, and at some point you want to escape the planet, well, you're moving on a circle around the Earth, and at some point here, you decide that your spacecraft has to go away, and it's to escape. Well then, what is square root of 2? This is about 1.41. It means that you need to give a 41% of your v-circular boost to gain that additional velocity you need, right? Does it make sense? If I am in this particular position, r, and I decide that I don't like the circle anymore, I want to go away, I want to go on a parabolic path and go to infinity with 0 residual relative velocity, this is telling me, well, your velocity is not sufficient. You need to bring it to v escape, which is 41% more than v circular. And if you are at the height of the International Space Station, that is 7 kilometers per second, so you have to give a boost that increases your speed about, what, 3 kilometers per second? And that's a huge one. Okay? If you are in geostationary orbit, which is 3 kilometers per second, that's a little less, still a big one. Delta V's, as we'll call them, of kilometers per second require pretty powerful engines. Okay? So that's why probably you don't decide, if you need to really go on an escape trajectory, you don't do it from a very low Earth orbit. Probably you do it from a higher one if you can get there. It's always a matter of trade-offs, but it's probably not a good idea to do it there, because there you may need to fight aerodynamic drag as well. So, but that's the kind of mindset that we'll have when we'll start maneuvering, especially with impulsive maneuvers. We will assume that here something happens that all of a sudden, without changing the position, is so quick that I can increase my velocity from v circular to v escape without changing the position, right? This is so fast that the only thing I see changing is the velocity. All of a sudden, I get a push so intense that I can change the velocity without changing the position too much. And so I call it an impulsive maneuver, and that's how we design the corrections that we need to make. Okay. Any questions, comments? I have an actually simple exercise that this is another uncollected homework if you want. Do the following. Simulate. So this is in ODE 45. Let's see, what am I saying here? Half circular trajectory or orbit at a height of 500 kilometers. Okay, this is height. No, a major mistake would be sticking that into an ODE 45 as an R. The Earth as a radius, which is 12 times that. So, okay, that must be a height. If you see that, there is no ambiguity. Cannot be the radius. So just let it go for half an orbit, just for fun, and then do what I am doing here. Just boost to escape. So this will be some if condition in your equations somewhere, probably in the equations of motion that you call from ODE 45. So use the ODE 45. Basically use what I gave you already. Just simulate something that is circular, and then after half a period, or even earlier than that, I don't really care, try to implement a change such that the velocity all of a sudden increases of 41% and see what happens. You should not come back. Okay? And another interesting feature of these parabolic trajectories here, again, you'll prove to yourself that they're parabolic. It's in the book. It's all Cartesian coordinates, nothing special. The flight path angle also, this is something that can be easily demonstrated. I don't think we need to go through the same steps for everything here. Another nice feature is that the flight path angle here, so the angle between the local normal and the velocity vector, this is how we define the gamma. It's always half of the true anomaly. That's what happens for a parabolic path. Questions, concerns?
Is that theta over 2?
It's theta over 2, yes. And I think that's all I want to tell you about parabolas. Much more interesting, in my opinion, are the hyperbolic ones. Because if you fly on a hyperbolic path, you do have actually, you still go to infinity, but you do have some residual velocity relative to the planet that you can use to maybe reach another planet. So your Keplerian orbits expression still is the same. Actually, E comes back into the game here. But there is an angle before pi where that denominator goes to 0, right? Can I erase? Well, I can still use this side. So when does this go to 0? When the theta is arc cosine of 1 over E. And so we call this theta infinity because that's the true anomaly where your arc goes to infinity again. Before it was a pi, right? Because E was 1. Now it's a little before pi because, I'm sorry, this is a minus here. It's before pi because being this bigger than 1, you can convince yourself easily that now this angle has to be between 90 and 180. So it happens a little earlier than 180 degrees, depending on E. I'm going to leave this down there for a little longer because I want to use this side. So what do you call, if you have a curve that approaches a certain line at infinity, what's the name of that line? Yep, that's what we call this. This is the true anomaly. True anomaly of the asymptote. Okay, and so let's draw this, and I'll try to make it big so that hopefully I can fit all this stuff. So I have the two asymptotes here. Line of ups. So this is my line of ups. This point here in the middle, call it C. Let's see, the planet is here, M1, we call that point also F. We've done the same for elliptical trajectories. Okay, so this is the real trajectory. So your satellite may be coming from somewhere down here, and it goes to infinity, and this is my angle theta infinity, right? Now, if you actually plot this expression for all values of theta, you do get a vacant branch. On this other side, if you plot that expression, you get a symmetric line where, of course, there is nothing. A satellite cannot travel on two different branches of the same hyperbolic path. It doesn't make any physical sense. But we still plot it there to define a few quantities. So this should be symmetric. Really doesn't look like, but that's the idea. Okay. So let's give these points some names. Okay, this is C. This is the focus or the mass, the attracting mass. This will be the perigee. And this is actually, this point down here, you get it sticking the pi value there. It's the apogee. You get a negative number. We'll play with it. And so this is just definitions that are given. People use these as conventions. We call this distance 2a, as we've done for the ellipse. And what else do we care about? We care about this angle here, beta, or this angle here, delta. And let's see what they are. Why are all these quantities important? Well, this is the direction where you're going to go eventually, right? With respect to your planet, with respect to your eccentricity vector, that's the direction you're going to point. So you're leaving the planet and you're pointing in a very specific direction. Before it was at pi, but then you would stop for the parabola. In this case, when you get to pi, you don't have any residual velocity. Here you will. So you will leave the planet at that particular angle. This angle here has a name. It's called the turn angle. Why? Because this is actually used all the time in interplanetary trajectories. You've probably seen a bunch of movies where they say, fly by, I use the planet to go on another trajectory. That's what they do. You're coming, this is your planet that you're going to exploit to change the direction of your vector, the velocity vector, without boosting. You don't need to boost here. If you come in, at the right distance, you can play with that distance so that the turn, because the velocity vector is coming in as the asymptote here, and due to the presence of the planet, eventually you're going to leave that planet's sphere of influence at a different angle. And the change in velocity pointing is delta. So you can actually change, you can maneuver with planets. That's actually is done. That is actually done. It's okay, so what is delta? Again, I really don't want to prove too much stuff today, so I leave it up to you to do it. It's just trigonometry here. Is the arc sine of twice the arc sine of 1 over e. And that's all we need to know. A, that I want to compute probably. A is going to be, if I have defined it this way, well, 2a is going to be the difference between the distance between f and a, and f and this point, and f and p. F and p is r at perigee, which is h squared over mu, 1 over 1 plus e. R at apogee is h squared over mu, 1 over 1 minus e. What do you see that is strange? Don't see anything strange? This is negative, right? And that's okay. This is what happens because you basically get negative values from that expression because here there is really nothing physical. So we accept it this way, and we'll just say that 2a, since I know that it is RA somehow involved, I just put the norm of it, RA minus RP, and so I get, what do I get? Minus h squared over mu, 1 e minus 1 plus 1 e plus 1, and in the end I get, well, something very similar to the, to what I got for, for an ellipse, right? I think the ellipse was 1 minus e squared, but at least this is positive now, so I can use that. I think there is a 2 that I need to simplify. Yes. So this is actually leading to a. If you do all the steps here, there will be a 2 that you can simplify. So why do I care about this? Because I'm going to do the only thing that is missing, really. It's the energy. And then talk about velocities. And show you what happens on an hyperbolic path. Why I'm leaving the planet and I do have some residual velocity. Well, your energy is still the same. Still what we had before. You start from minus 1 over 2 mu squared h squared 1 minus e squared. And if I compare with that expression that I have for A, something that we have done with the parabola for the ellipse as well, you can show that this is mu over 2a. Just compare A and that expression have the h, the mu in common, the e squared minus 1, flip it, change the sign. It's nothing new. Am I going too fast? I'm just redoing the same things that I've done for an ellipse. I'm just going to the final results. And those are the things that you're going to use anyways. There is actually, I'm going to show you, after I'm done with this, I'll pull down the projector. There is one page in your book where they say, yeah, we know it's a lot of formulas, but here are the ones that you really need. And it's just a bunch of them. It's just, you just need to know what these curves look like and the main geometrical features. You know, semi-major axis for the ellipse, the 2a here that, you know, we can still call it a semi-major axis if you want, the a. The theta infinity, you need to just know that these things belong to different shapes and how to compute them. Yes, there was a question down there? Maybe? No? Okay. Now, what's different? So for circle and ellipse, we got negative energies, right? Was it minus mu over 2a? And a becomes the radius if it's a circle. Still holds through, so this is a negative energy. So these are closed, if you want, I just call them closed orbits. We have two kinds, circles or ellipses. For the parabola, we said 0, so this is parabola. Well, now we have that. What kind of energy is this? Positive, negative, 0? It's positive. Hyperbolic paths have positive energy. You need to have positive energy, mechanical energy, the way we have defined it so that you can go away. Now, this thing can be equated to what the definition of energy is, which is still the same, v squared over 2 minus mu over r. Okay? And so, all right. What do I want to do? I want to do something else. Can I erase here in between? Are you done copying this? Maybe? So what is the velocity that I get at infinity? Let me compute that first of all. If I go at infinity, I get, the energy is still there. It's mu over 2a. That's always the same, and it doesn't change. If I am at infinity, I have v infinity squared over 2 minus mu over infinity, right? The radius at infinity is 0. So my v infinity is square root mu over a. So look at that expression. Multiply both sides by 2. Move these on the other side. Well, let's do it. You get v squared over 2. It's also equal to mu over 2a plus mu over r. Put a 2 here. Okay? So I get the v squared. Let's use these two together. I get the velocity squared at a generic point, because here I have a generic r, right? It's equal to the square root of mu over a, but that's v infinity squared, plus the square root of this We've just computed this, right? So this is v infinity squared plus v escape squared. So at any point, I can go over this again if it wasn't clear. So actually, let me do it. The energy for an hyperbolic path is always something you can express like this, and it's a constant. Energy is constant for any trajectory. Once you compute it, it's what it is, unless you start maneuvering. But if you don't, this is what it is. And this is a geometrical parameter of your orbit. So I can equate that to the generic definition of mechanical energy at a generic position r with respect to the planet and corresponding velocity, right? So this should make sense. Then I went here and I said, okay, let me see what happens at infinity. At infinity, I can compute the velocity. It's going to be this. Fine. I'm going back here, and I'm still computing the velocity at a generic location, and just manipulating this expression and knowing that that's v infinity, this is what I get. Here I just remember that if I am at a distance r from a planet, the square root of 2 mu over r is the escape velocity. That's what you will need to barely escape the planet. Go away with no residual velocity. Well, here it's a little different. Your velocity squared at any point on the hyperbolic path is, actually let me write the escape first, is the velocity of escape squared, I mean this is a relationship with the squares of course, plus this additional v infinity, which is what you would have once you are really on the asymptote. That is also called the I think the infinity is called on your book the excess, hyperbolic excess speed. That's what they call it. There are various ways, but basically what it is what you're left with after you've traveled enough on your hyperbolic path. So if you want to escape the planet and move as the planet, you need square root of 2 mu over r. If that's not enough, you need a little more. You need this. Well, that's actually what you decide. You decide how much of this you want. Right? Yes?
When you say move out of the planet?
By out of the planet, say, for now it means really going to infinity. Going to a radius that is infinity, in principle. This is all, for now we're living in a vacuum. We have planet, satellite. Reality is that it's never the case. At least we have the moon. Or if we don't have the moon, when you start going far away, there are other effects, other planets, the sun. So that is not really true. But this is the approximation that we used to determine how much we need to accelerate the satellite so that we can make the escape, which again means that you're not going to come back. That's the point of escaping. You're not on a closed path. You're not coming back. That is escape. Then on top of escape, which is hyperbolic paths, not only you're not coming back, you have a residual relative velocity with the planet, with respect to the planet. So in other words, if you look at the trajectory of the Earth around the sun, again, if you're talking about satellites of our planet, let's say that this is the sun and this is the Earth. So if you go on a parabolic path, you may basically at some point have your satellite that is somewhere flying around the sun on the same trajectory. Instead, if you don't, you may actually have the satellite that's just going away on some other trajectory, maybe going to Mars or somewhere else. So you need the excess speed to go on a different path. The escape is only enough to to obtain the condition of not coming back. The excess speed is what allows you to go on an interplanetary travel, pretty much. Yes? Is there a question? No question? Is everything clear? No? Maybe? You're not impressed? You watch too many movies where they use this stuff all the time? I still have to watch The Martian, by the way. They say that they have an amazing astrodynamicist in that movie. I don't know, I haven't watched it. I read the book. Well, that's the last thing before I... Well, okay, we have time. You have a question?
Yeah, how did you use the
Oh, yeah. There is no square root. Yes, thank you. The V escape, remember, the V escape is square root of 2 mu over r. If I don't do the square root, then it's V escape squared. Thank you. Any other questions? One last thing that I really don't need to spend too much time on is the perifocal. I think I mentioned this last time. Coordinate system. Just to be thorough, I think your book has a subsection about it, but we have defined it already. If we are in the orbital plane, which means the h vector is pointing at us, and we're looking at the trajectory from above, and let's say that it's whatever it is, circular. Well, circular would not apply here too much, but say that it's eccentric. There is an e vector, and the norm is between 0 and 1, for example, but it does apply to all shapes. The perifocal frame is defined as a unit vector in the direction of E, so we can call this I, the x direction. A unit vector that comes out k in the direction of, I don't know why I'm writing so small, sorry, in the direction of h coming out, and then the cross product of the two gives you the j. That's the perifocal that your book calls reference frame. It's not a reference frame, it's a coordinate system. There is an origin, which is your planet, and 3 directions, they are your coordinate axis, so that is a coordinate system. That's why I stick to the book, but sometimes I don't agree too much. It doesn't make a huge difference, but people use reference frame and coordinate systems interchangeably, but it's not really appropriate. So that is the perifocal coordinate system. It's what we have used to demonstrate that the elliptic trajectory is an ellipse. Remember? That's what I've done last time. And that's what you should have used to solve the uncollected homework. So let's look at that one. You don't have any more questions? No? First, let me show you that page on the book that really, we're back. Yeah, the projector is not working now. Is it? If I don't hook it up, it doesn't work. Yep. Okay. Yeah, I just want to show you that page on the book that collapses everything into a few formulas. It doesn't mean that that's the only page you need to know of. It just helps you organizing things. So this is a nice page. Again, this is version 3, so I don't know exactly where this is in your version. It's probably the same page. You can write down the equation number probably. So this is true for all orbits. Yes. I'm going to touch the screen. This is true for all orbits. And then for those that are closed orbits, again, the E equals 0 is included. That's the same major axis expression. That is your energy expression, minus mu over 2a. It's a negative energy, and it's always equal to kinetic plus potential. That's the period of your elliptical orbit. It does give you the period of a circular one when a is the radius. And this is another way to compute eccentricity. For a parabola, it doesn't really give you anything else other than the energy is 0. They could give you the escape velocity. I would have listed that. And then for hyperbolas, you get the asymptote. The turn angle, yeah, this delta is something that I did not mention to you. It's just the distance between. So if your satellite is going this way, delta is the distance between the asymptote and the line from the planet parallel to the asymptote. It's this distance here. I think it's called aiming radius. So it's there for you if you need it. And a nice image here, I could never do this on a board with chalk, so it's good to have it here, is this that shows you for different eccentricities what happens. You start from circle, you go with higher eccentricities, you get eccentric trajectories more and more until they don't come back anymore, they don't close anymore, and that's your E equal to 1 right here. And as you change your eccentricity, you're changing the true anomaly of the asymptote. So by playing on the eccentricity of the hyperbolic path that you want, you decide what the turn angle is, right? You decide the angle between the asymptotes, and you decide. So that basically drives how close you need to be to the planet to have the right turn. So do open this book and try to solve the simple exercises that are actually all guided exercises that they have on top of the things that I tell you to do in Matlab. In Matlab it's a lot more fun because you can do the same things, and Matlab does it for you, plus you can plot. Now, what I ask you to do is this. So the part where you start using the perifocal frame is where I ask you to plot the trajectory using the true anomaly expression, which is, once again, this one. Okay. All right. What do you do? Well, you go to this basis here. You know that the norm of this vector is given by that expression at a given theta. And so your r as a vector is given by r cosine of theta plus on the I direction plus r sine of theta in the k, in the, what did I call that, j direction. So that is something that you should implement in Matlab. Let's see how it is done. So this is old stuff. You have it, you have it, or you have it. ODE 45. So this is the new stuff. Question 1. Very simply, I take cross product of initial velocity and position, and I get h. You must start from h and e. Those are the first two things that we've proven they're constant for a Keplerian orbit, right? You start from those, and then you compute everything else. But you have to compute those. And recall that they are two vectors, so they have 3 components each, but they are normal to each other. So they don't give you 6 constants of integration, they give you 5, because there is a relationship between the two. They are normal. We don't have time in the picture for now. I am plotting everything with theta. The only way we're dealing with time is by integrating the differential equations. But next week we'll start seeing the relationship between the true anomaly and time. Even if you have to integrate that numerically, it's just one equation instead of integrating 6 differential equations as you've done with ODE 45, right? So all this stuff that we have done, playing in the same, just in one plane with those geometric quantities, it's great because you only need to tell me how theta changes with time. Everything else is set, okay? So, but you have to compute the h and e. And now here I am defining exactly what I'm telling you there. Z hat is h. It's the vector h normalized. It gives you the direction out of plane. X hat is the e vector normalized. It gives you the direction of the line of ups. And j is, well, right-handed, so k cross with x hat. I think that's what I'm doing. Yes. Well, I call it z, I'm sorry. Z hat, so let's be consistent. This is z hat. And this is what? What did I call that? Y hat. Okay. 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 Now I do have the perifocal coordinate system. They don't change. H doesn't change, E doesn't change, Y doesn't change. So you define those once and for all. And here I just decided, okay, I want to use this expression right here. And since I don't know how theta is changing with time, I just decided to have 360 values of theta. They go from 0 to 2 pi. So that's what I'm doing with this instruction that you've probably seen before. Theta is a vector of values from 0 to 2 pi spaced by 360 points. And here is the norm given by the Keplerian expression right here. That's what I'm doing right there. And then I have a for loop that does calculate this vector as a vector for 360 times. So it goes around one orbit, and it gives me positions. Now, what I hope it's clear is that the points you get in 3D, x, y, and z that you get from ODE 45, so the r vectors that you get from ODE 45 are different in general from the R vectors that I'm getting from the theta approach right now, because I have no idea. The ODE45 is integrating in time and is creating that T out vector right there on top. And it's deciding, I mean, I can decide where I want the outputs to be given at which times. But even if I do that, even if I tell ODE45, okay, give me position and velocity every 10 seconds, you can do that. There is an option to do that. So it will output position and velocity every 10 seconds. I have no idea how that time relates to theta for now. I don't know this. I don't. For now, I have no idea, right? So, but you can still plot trajectories in 3D, right? So what Matlab does for you, it takes a bunch of points and then connects them with a line. So that's why if you plot these R vectors versus the R vectors that you're getting here from ODE45, you do get the same line if you've done everything correctly. So let me see. Yeah, I think it stops here. So if I run that, I think I showed you this before, right? I get, I haven't done a full orbital period in ODE45. I could change that. But so if I remove these, you see the black one is the one I obtained with the Keplerian expression that I just raised. The red one is from ODE45. So I was asking you here to basically verify that they are the same, and you do a plot and you can really see that they are on top of each other. That is one way. Now, why am I asking you to do 0.3? For the same reason that the positions that ODE45 is generating and positions that the theta approach are generating for now have nothing to do with each other. They are at different times. That's what I'm trying to say, right? Since I don't know this relationship, these are different times. Now, plotting positions in space, you obtain a trajectory. Plotting velocities, you could, but I can't really give a name to the plot that you get. So just to make things a little more entertaining, I'm asking you to get this bunch of vectors that you get from ODE45 and extract the corresponding thetas. Once you have the corresponding thetas, you can use those thetas to compute the velocity according to the parametric expression. And so you can compare velocity against the same velocity. So they are the velocities at the same true anomaly, and basically at the same time. Making sense? No? You can stop me? Is it clear why the positions and velocities I get from integrating numerically are in principle different from the ones that I get just choosing theta values randomly, which is what I'm doing here. I just chose 360 points equally spaced. I could have chosen thetas at different locations, 0, 10 degrees, 35, just random points, right? Since I don't have a relationship between theta and t now, I can't make a relationship here, a one-to-one relationship, right? So for the velocities, I'm just telling you, okay, do this. Extract the true anomalies that correspond to what ODE45 gave you. And so with those now, you can compute velocities with the other technique, and you can compare them. So that's what is coming afterwards. So what am I doing here? Okay, since I have to start from what the ODE45 is giving me, here I'm computing the size of this vector. By the way, have you, this is a very powerful tool, debugging. If you've never done it before, I do strongly advise that as you start developing software, and as soon as you get an error or something that you don't like, you go and start putting breakpoints, and you go line by line and see what's going on, because that's the only way you can find the error. I've seen people just running the same software over and over for days and weeks without ever debugging. They would just bang their heads against the wall, not finding the error, because you don't find it unless you debug. That's how it is. Because this is just a bunch of lines of codes. You miss a comma somewhere, you swap the order of variables, and nothing works. So here, I'm computing the size of the vector that the ODE45 is giving me. And now here, what I'm doing is I'm trying to find where is the apogee. Now, I know that this trajectory I'm simulating for just one orbit. So I'm going from perigee. So actually, the initial conditions are at perigee, if you check. There I go around, half an orbital period. I hit apogee, and then I come back at perigee. So with that instruction here, I'm computing the maximum of the norm of the radius vector. And since it's a bunch of points. What this is giving me is the maximum value, which is this in kilometers, and this is telling me in which location that is happening in the vector. So if the size of t out or y out, it's the same thing. It's a vector of 997 points. Well, at point 527 is where I have the highest r value. That's what I'm finding. Okay, so I know what it is. Okay, I'm going to use it later. Now this is the step that I was discussing before. Now I'm going to compute for each of those r locations what is the theta. And how do you do that? Well, the theta, we define theta. We said theta is the angle between the eccentricity vector and the position vector. And so we know by definition of dot product that this is what happens. R dotted with E is the product of the norms cosine of the theta angle, which means that theta is the arc cosine of the dot product between the vectors, and that's divided by the norm, right? Okay, and so that's exactly the argument that you see at line 77. This is argument. This is my argument variable. I know I should choose shorter names for variables, but that's what I have. Why do I compute that before computing the arc cosine? As I told you, if you don't do that, actually, maybe we can try to see what happens if I don't do that. Let me see, quit debugging. Yeah, let's just do this. Comment this out, and comment this out. I don't know if this is going to work. Let's see, try. Yeah. What did I call that? Theta, the theta ODE 45. So these should be the true anomalies that correspond to the positions that the ODE 45 gave me. See? That's great. I have complex true anomalies. Because that function sees something slightly bigger than 1 at some point because of numerical errors. It may be 1.000000001, and it gives you theta. And so that is something you find out only if you debug, believe me. So once you know that the function has that problem, well, you go back and you fix it. I don't know why it does that. I think there is a need in some cases to actually have that kind of output. But here I'm preventing the function to do that. So I compute the argument of the arc cosine function first, then I check if this is actually greater or equal to 1. And if it is, I just say, argument becomes the sign of itself. So it's 1 or minus 1, no more than that. It cannot go outside that range. And so I know that now using this instruction is going to give me a real angle, not a complex one. That's what software does for you. It creates different types of problems. You think you don't have to think, but you have to think in other ways. So, and then this is why I computed that k value where the apogee is happening, because I actually want theta to go around 0 to 2 pi. I think it's convenient. But since the arc cosine function returns an angle between what? 0 and pi. So it's going to start giving me the same angle once I passed pi, so I correct for this. After the apogee, which is at pi, I say, okay, the true anomaly is actually 2 pi minus that. So in other words, if this is your planet M1 and centricity vector is pointing this way, and you pass the apogee, which is down here, maybe you are down here, right? I want this. I want something bigger than pi. But the arc cosine function is going to give me minus this angle. So I correct for that. Not sure if it's really needed. That's what I did. Okay, and now I have the true anomalies that correspond to those values. And here I'm using the definition of velocity that is parametric with the true anomaly. And I think we're done. V radial, go back to your notes, is a function of the true anomaly. V perpendicular is a function of your true anomaly, and here I'm building up the vector. And how do you build up the vector? Well, what is the V, the radial direction? Okay, this is UR, and this is u perpendicular. Your v is v radial norm, okay? ur plus v perpendicular, u perpendicular. What is this? This is r normalized, right? And u perpendicular, we can get it as h crossed with r normalized. And I think that's what I'm doing there, I hope. Yeah. And that gives you the velocity. The last thing that I'm doing down here is comparing this velocity with the output of the ODE 45. You get, of course, a bunch of vectors, and I check what is the biggest value in that vector, and it's something 10 to the minus 8. So they are identical vectors. So I'm getting the same velocities. I better get the same velocities. Questions? No questions? How bad do you want this Matlab file? I don't know if I can. I'll think about it. If you have questions, let me know. But this is very relevant, just to let you know. Have a good weekend.